functions.
Okay. Which also means logarithms.
Yep.
Okay.
So I'm pulling out my textbook right now.
Okay.
So it's from a lot of this stuff is stuff I can really verbalize well.
Is it in a graphic form?
No, it's like long. It's long word problems.
Okay. You want to take a picture and send them to me real quick?
I can try. My camera's crap.
Huh.
Well,
okay. You could try reading them, and we could. Usually long word problems. It's hard.
They're just word problems in general are just going to be harder with this.
Well, go ahead and try reading the first one while you're trying to take a picture of some.
All right.
Let's see if we can work on it.
In 1965, the federal debt of the United States was $322.3 billion. During the next 30 years, the debt increased by about 10.2% each year. Write a model of the given amount D in billions of debt in T years after 1965. How much was the federal debt in 1980? Graph the model. Estimate the year when the federal debt was $2.12 billion.
Okay, I think I can figure out that without seeing it. So the federal debt dropped by 10.2% per year. Now, first of all, let me ask you, they've taught you all three formulas for doing this, right? Annual, more than annual, and continuous?
Not yet.
So they've just taught you this one.
No, so just annual.
And it makes a difference when you're doing problems like this. Because first of all, the debt doesn't drop 10.2% at the end of the first year. It drops gradually over the year.
I don't know if they've taught, I don't know if it's different, but they've also taught us P times 1 plus R over N to the Tn power.
Okay, well that's the second one. Here, let me write all three of them. Hold on a second. What happens here? Why does this... That's weird. My eraser tends to not work periodically. Okay, let's talk about this for a moment. And finally, the third one equals okay. The top one is if something is being compounded yearly, like a bank account.
Mm-hmm.
And it's artificial in the sense that nothing in nature compounds yearly. Only human creations like bank accounts that compound yearly are going to use this one. Okay. Yeah. Bank accounts also might offer you monthly compounding or quarterly compounding. In other words, more often than yearly. And if that's the case, you use that, where n is however many times it's compounded. So if you were compounding monthly, n would be 12. Hold on a minute. Let me close my door so my dog doesn't drown us out.
All right.
And thirdly, this is continuous compounding. And that's the way nature works. In other words, if you know that rabbits population increases at 10% per year, well, it's continuous. Or if you have bacteria growing in a petri dish, it's continuous. Or if you have uranium-238 that's decaying, it's in a petri, or it's continuous. And this problem here is also continuous. It's the continuous decay. Now, I'm not sure that they necessarily want you to use this third formula because they sometimes like to keep it simple and straightforward, and they use this first formula, especially when they word the problem like this. In other words, they actually do kind of indicate that it drops at 10.2% per year. Okay? So my guess is they want you to use that formula right there, but you could also use continuous. Now you'd get similar answers, but they wouldn't be the same. Do you happen to know which one they want us to use for sure?
Not for sure, but I'm guessing since it's doing years, I'm going to guess the top one.
Yeah, me too. That's what I'm going to guess too. Okay, so let's...
Because it's not saying how many weeks after.
Yeah, no, I get it.
So you wouldn't use the second one.
They're trying to simplify it, but in their simplification, they use the wrong formula. That's okay. So the amount that our debt, which starts at 322.3 billion, I believe, and it's going to decrease, which means R is negative 0.102 each year.
Said it increased each year.
I'm sorry, what?
Said it increased.
Oh, it's an increase.
Yeah.
Okay, so it's a plus there. To the T number of years, and they wanted to know what the debt would be in 1980. Are you sure it's an increase? Because the last part of the problem you told me is when will the debt get to be 2.12 billion, which would indicate...
Well, you have to, that's after you graph it.
But that's a serious decrease. In other words, we're going from 322 billion.
Oh.
Is this 2 trillion, maybe?
Yeah, it's 2 trillion.
Okay. Which you would get to at some point in time if you started with 322 billion and you increased it by 10% per year. But the first question they want to know is what the debt will be in 1980, correct?
Yeah.
So what is T for 1980?
15.
Correct. And it's not always clear that it's the second year minus the first year. You kind of have to make sure you're not off by 1. In other words, 1966 would be 1, 1967 would be year 2, and so forth and so on. So you realize that, yeah, you can just subtract the 2 years, and that's what T is equal to. So the amount of the debt is going to be 322.3 billion times 1.102 to the 15th power. And billion is not a variable, it's just that. So do you have your calculator?
Getting it out right now.
First thing you want to do is the right part. 1.102 to the 15th power. Take that answer, multiply it by 322.3 million, or billion rather.
$1,383.52.
That's billion. And that's 1.3 trillion. Okay. So the second part of the question says, when will the debt hit 2.12 trillion, correct?
Mm-hmm.
So the left needs to be 2.12 trillion, and that's going to equal the starting amount in billions times 1.102 to the t. And we're trying to solve for t.
Mm-hmm.
And this is where logarithms come in. What's the first step on solving this problem right here?
Dividing by 2.12.
Well, dividing by this.
Oh.
Right? In other words, we're trying to get the right side narrowed down so that we can solve for t. Notice that this is not an algebraic equation. There is no kind of algebraic process that lets you solve for t, even though it's the only variable. The fact that it's in the exponent is what makes it an exponential equation. And you have to use logarithms to solve this. Well, in order to use logarithms, I want to isolate that part right there. Okay, well, the way I isolate that is to divide both sides by this coefficient. This coefficient is not being acted on by that t. So I want to get rid of that coefficient. So divide 2120 by 322.3. What do you get?
Second, I was in the wrong thing. 2.12. You got 0.006.
Okay, so you get 6 point what? What's after the 6?
5.
Anything else?
7, 8.
So that is what 2.12 trillion divided by 322.3 billion. Because remember what 2.12 trillion was? That was that number right there.
Mm-hmm.
In other words, 2,000 billion. Okay, so when we do that division, we better get a number in the neighborhood of 6. And we did. Okay, so now that is equal to 1.102 to the t power. How do I solve for t?
Root t both sides.
Huh?
I don't know.
It's a good idea. I like it, but remember logarithms. You have to solve exponential equations by using logarithms. And the reason is if I take the log of both sides, in other words, if I take the natural log of that side and the natural log of that side, now I can apply the properties of logs that allows me to bring this exponent down in front. So you end up with this equals t times natural log of 1.102. And notice that that's just a number you get out of your calculator. That's just a number you can get out of your calculator. So now we've turned it into an algebraic problem. In other words, we can solve this one algebraically by dividing both sides by natural log of 1.102. So I'm going to divide both sides by that, and that's going to give you your answer. What is that?
1 second.
And I could have used
I,
any log. I
I've
did.
never used logs before, so
You've never done logs before?
no.
Okay. Well, we know what to do with the next 15 minutes. Um, what kind of calculator do you have?
An Inspire.
You have two log keys. One should say ln and the other says just log.
Yeah.
Well, do the ln. Follow it with 6.578 and divide by ln 1.102.
So 19.39.
That's how many years it's going to take for this 322 billion to grow into a 2.1 trillion size debt. 19.39 years. All right, let's talk about logs. Every discussion of logs begins right here. For example, correct?
Mm-hmm.
What is the logarithmic, the equivalent logarithmic expression for that? Y equals b to the x. In other words, logarithms are just another way of expressing exponential equations.
Mm-hmm.
Okay, and you only have to remember one thing. Logs are exponents. So I can immediately write that. Now, where does the b and where does the y go? B always goes down there.
Okay.
And there's only one place left for the y, and that is the argument of the log. So these two are equivalent. If I wanted to write this expression over on the right, 8 equals 2 to the third, in logarithmic form, how would I do it? What is it?
I have no clue.
Well, what's the first rule of logs? Logs are what?
Exponents.
So it's got to be the log of something equals 3, right? Because 3 is the exponent. Okay, what's the base? What's b?
2.
Okay, that goes there. And the only thing left is the 8. That goes there. So these two are equivalent.
Okay.
Log base 2 of 8 equals 3. Same thing as saying that 2 to the third power equals 8.
Okay.
So you want to always be able, the secret of logs is being able to switch back and forth between those two things right there. Okay? Let me give you one. Log base 3 of 9 equals 2 means what if you were to express this exponentially?
That the 3 cubed equals 9.
3 squared equals
3 squared equals 9.
So. In other words, it's always the number. The way I like to think about it, although it doesn't always work,
the number on the other side is the equal size.
The number on the far left raised to the number on the far right equals the number in the middle, which is fine, but sometimes they'll give you this, which is just as valid. Now it's not the number on the far left anymore. In other words, what it really is the base raised to the exponent equals the argument. That's what this says, is the base raised to the exponent equals the argument. And that's what this says also. All right. So, and you absolutely have to be able to go between these two to be able to do these problems you're trying to do, and a lot simpler stuff. these problems, it seems to me, are the harder end of logs and exponentials. You should have an easier end of it that we should look at. I think. I'm not 100% sure on that. That they would not start you off here. Just a second, let me...
What they've started having us out do is use graphs to find like the 2.12 billion.
Okay. Let's talk about that. Huh, interesting. So they haven't really given you logs yet.
No, not really.
Okay. Well, they will, and then that'll come in handy. But, so they gave you the graph?
No, so you'd plug the graph without the value of t into the graph.
Okay, so in other words, we're doing this graph right here.
Yeah. You have the 322.3.
Right. But essentially, these kind of graphs all look like this. Okay? In other words, the graph I've just drawn could be y equals 2 to the x. It could be y equals 10 to the x. It could be y equals 17 to the x. As long as this thing is greater than 1, it's going to go from lower left to upper right. And it's always going to go through this point, which generally is 0, 1, no matter which of these three functions I'm looking at. They all go through that point, because remember that any number to the 0 power is 1. But if I just drew the graph and the point that it goes through, you'd have a hard time distinguishing between that one, and that one. You wouldn't know without any more data on there.
Mm-hmm.
But we know that this will be the general shape of our graph. Now, when there's an a sub 1, then this point becomes a sub 1. In other words, when t is 0, you're left with 1 times a sub 1. So that point right there is 0, a sub 1. And you can figure out your answer by the graph. In other words, here's what the horizontal axis is, the t. This is t, not x.
Mm-hmm.
And this is a, not a sub 1, a. So the amount at any point in time, and we had to figure out after 15 years, right?
Mm-hmm.
So we're looking for what that is, and we figured out that that was 2.1 trillion, when a sub 1 was equal to 322 billion. Now, there's a caveat to these exponential graphs, and that is that if I have y equal b to the x, or the t power, we'll call it, and b is a number between 0 and 1, then the graph tends to look like this instead of black. In other words, the whole thing as to whether it's increasing or decreasing depends on whether b is less than or equal to 1. If you have a number greater than 1 and you exponentiate it, then it gets bigger as t gets bigger. So this, you're taking a number greater than 1, 1.102, and you're exponentiating it. So the bigger t is, the bigger the a is going to be. But if you have a number less than 1, for instance, 0.95 to the t power, then as t gets bigger, the answer gets smaller. And you end up with my red graph.
Mm-hmm.
Notice that when you take let's take an easy one, 0.9 and square it, becomes 0.81. Square it again, becomes 0.72. Square it again, becomes 0.6. Notice the answer is getting smaller and smaller as t is getting bigger and bigger. So whether these things represent exponential growth, the black curve, or exponential decay, the red curve, merely depends on whether b is between 0 and 1 or greater than 1. So they wanted you to solve this graphically because they haven't taught you logs, which teaches you how to solve it not quite algebraically, but mathematically,
Mm-hmm.
which is always easier to do. In other words, if you pull the answer off of the graph, you're going to be guessing to some extent. In other words, it's hard to read precise numbers off of a graph. But I get what they're doing. They're doing it graphically because they haven't really taught you logs yet.
Mm-hmm.
Didn't you get a little bit of logs in Algebra 1 and geometry or not?
No, I didn't get any logs. We got some
Trig.
yeah, we got trig, not
Okay.
logs.
So you never have had logs. Okay. Well,
Never had logs.
we got a lot to teach you with logs. No, not really. I could probably teach you everything I know about logs in 1 full hour. And that's going to let you get through the next 2 weeks worth of math material, which is good because that's 2 half hours. So, but remember what I said. In other words, it's fairly easy to do it off of a graph, right? I mean, there's no math involved there. The key to logs is this relationship right here, because you're going to have to go back and forth between those two. All of the log problems they give you, you're going to have to convert the exponential to logarithmic, and you're going to have to convert the logarithmic back to exponential. So just remember that logs are exponents. As long as you remember that phrase, then you can't really make a mistake when you go from the y equal b to the x to the logarithmic expression of it. And the beauty of the logarithmic is it gives you a way to solve exponential equations. What makes this an exponential equation is the variable is in the exponent. That's the difference. In other words, the difference between y equals x squared and y equals 2 to the x is huge. This is algebraic. This is exponential. All has to do with where the variable is. And the moment the variable gets in the exponent, the only way to solve those kind of problems is by using logs and knowing how to convert to logs. But logs are like any other process. You can take the logs of both sides of an equation. You can take the log of the left side as long as you take the log of the right side. That applies pretty much throughout math. When you get to calculus, you can take the derivative of the left side as long as you take the derivative of the right side, or you can take the integral of the left side as long as you take the integral of the right side. So pretty much any mathematical process you can think of applies to equations, as long as you do it to both sides. Okay? Why don't we stop for now?
Okay.
And then let's make sure we do a session next Monday, because I can help a lot with logs. Logs can be very confusing at first, just because they sound like some foreign thing. But they're really not. And as long as you keep in mind what I have circled here, you'll be fine. And then there's a few rules for logs that are the same rules for exponents that you've learned. And you go from there. All right, Cole?
All right.
Talk to you next week.
Talk to you next week.